Hello calculus students, I'd like you to please open up your packet today to day 3, Trig Inverse. We aren't doing any derivatives or any of that type of calc work today, but we're reviewing a pre-calc concept that's essential to being able to do a trig inverse derivative. And that will work on a little bit next week. We need to learn one calc skill in order to do so. I'd like you to grab a different colored writing utensil. If you need to pause the video at this time, please do so. Alright, so I have the first two sketched out. I'm going to give you a moment to copy this down and then let's talk through it. Alright, so let's take a look together. Hopefully you recognize this first graph as our traditional sine graph going from negative 2 pi to 2 pi. This here is our sine inverse. Let's recall that an inverse function is where x and y switch. And so notice that's what was done here. If I were to take my paper and turn it sideways, that's essentially doing a flip with our x and our y. But then it also mirror images. So looking at this, if I started at 0 and tried to go to pi or 2 pi, is this a function? Most definitely not. It fails the vertical line test. And so we need to restrict what values we're going to plug in. And so in order to do so, what we would need to do is identify a section or an interval of the graph that we want to use. If I try to go from 0 to pi, not a function. But if I just go from 0 to pi over 2, also not good, because then I'm just including the positive values. Well, I could go from 0 to pi over 2 and then jump and say from pi to 3 pi over 2, but why have a jump in our graph when we can have a continuous curve? And so we're going to define it with being from negative pi over 2 to pi over 2, the values that we can have, and that's where our sine inverse curve comes from. Similarly for cosine then. For cosine though, if I turn it sideways, from 0 to pi, worked out just fine. It was a nice continuous curve. It gave us all the positive values, all the negative. And so then here for y equals cosine inverse of x. I don't have our tangent one graphed out yet. Let's do that together, please. So if I have y equals tangent of x, and we know tangent is not defined at intervals of pi over 2 because at pi over 2 our cosine value is 0, sine over cosine is tangent, dividing by 0 not allowed. So let's make this our pi over 2 this time, and we'll go to negative pi over 2, also an asymptote. Alright. Tangent at 0, 0. Tangent at pi over 4, this would be, is 1. Tangent at negative pi over 4, negative 1. And then our traditional tangent curve looks like our S curve, following the asymptotes, of course. All right, but what if I wanted to invert it? Let's take a look at how that works out. Now realize tangent does go on forever, so I do have these curves forever. And so I'm just going to roughly sketch this one in. Because when we take a look at it sideways, does that pose a problem for us? Well, yes, if I looked at the entire tangent function, it fails the vertical line test. But if I just look at this one interval, or one period of tangent at an interval of pi, or interval length of pi, we're okay. So let's get rid of this other one I roughly sketched in here. Just use that to show why it would fail the vertical line test and why we need to still restrict the component that we're looking at. So let's look at y equals tangent inverse of x. Okay. We're allowed to have this whole graph, so let's highlight that whole graph here. That whole part worked. And so that's the part that we're going to sketch on here. At pi over 2, we have an asymptote. Negative pi over 2, we have an asymptote will follow. And our x's are from the negative 1 and 1. When I sketch this, here is, oh, I better make this more reasonable. At pi over 4s is where we're at the 1s. And so we'll follow our curve this way. And we have our tangent inverse. So what that tells us is we're between negative pi over 2 and pi over 2. Same as our sine. Okay, let's flip the page here. Don't mind the geometry notes underneath. Okay, cosecant. What is cosecant? Cosecant, hopefully you know, is defined as 1 over sine, and so that's what we're going to have to look at it as. 1 over sine. And so let's graph this as y equals cosecant x. And how we did this last year, if it's 1 over sine, well, we best still look at from negative 2 pi to 2 pi. And so we have 4 tick marks. 1, 2, 3, 4, being our 2 pi and negative 2 pi. If I were to sketch on my sine curve, and I'm going to do it with a dashed line because this is not sine, it's 1 over sine, the reciprocal function. But having that on here helps us to interpret what the cosecant graph would look like. So our sine graph from the other side was this in dashed form, and hoping you can see that okay. Okay. Well, if I take the reciprocal, it's going to instead bounce off, but please note that in a reciprocal of 0, we get asymptotes, and so on the cosecant function at 0, and at pi, and at 2 pi, so any interval of a full pi, we have asymptotes. So let's sketch those in. And then this is going to bounce off. And this is our cosecant graph. Kind of messy here. We'll give you a second to jot that one down before we take a look at what would we use for the inverse. So let's turn this sideways. All right, well, if I go from 0 to pi, fails the vertical line test. I can't use that. I could use this piece with this piece, or this one with that one, but I want a positive piece and a negative piece together, and we'll try to center it around there. So we'll take a look at from negative pi over 2 to pi over 2. Now realize the 0 is not a component of that. We can't have the 0. It's an asymptote. The function's not defined. It's not in the domain. And so when I say what values are allowed, we can't include the 0. So with y equals cosecant inverse of x, we would have that our y would be between negative pi over 2 and 0, not including the 0, and then also from 0, not including the 0, to positive pi over 2. Let's create a sketch for this. I'm going to make the x-axis dashed because it is essentially an asymptote, as is our pi. We don't even go that far if that's pi, and negative pi. This would be 1, negative 1. All right, so now we need to sketch what this would appear as. From 0 to pi over 2, we have positive values, and it starts at the 1 and bounces off. Here we would start at negative pi over 2, would give me negative 1, and then follows the asymptote. And so that would be my cosecant inverse. Similarly to cosecant, we'll work through secant. Secant is 1 over cosine, so let's get a sketch of cosine going here. 4 tick marks again. Making it from negative 2 pi to 2 pi. And cosine starts above. And I meant to make that dashed. I'm going to go through and dash that one. Because we're not really graphing cosine, we're graphing secant with the reciprocal function, so I don't want that to be the most prominent on your graph. Okay, so we have a dashed function. Remember, wherever it touches the x-axis, that's going to create the asymptotes, this time at pi over 2, adding on intervals of pi, so 3 pi over 2 at negative pi over 2 and negative 3 pi over 2. It is symmetrical, it's an even function. And then sketch our secant graph. This time when we turn it sideways, if I start here and start at 0, if I go backwards like I did with the sine, not good. Fails the vertical line test, or horizontal I guess we could use if it's an inverse function. So I'm going to need to go from 0 to pi over 2 and then from pi over 2 to pi. I can't say that I'm including the pi over 2 because it's undefined. It's not part of the domain. It's undefined. So y equals secant inverse of x. Our y values, our range is going to go from 0, including the 0, to pi over 2, but not including the pi over 2, and then from pi over 2, not including it, to pi. And we'll sketch this one out. Remember, asymptotes at pi over 2. So if I'm spreading this one out a little bit, this is pi over 2 making this pi. And having 1 and negative 1. We know that at 0 for cosine our value is 1, and then we have to follow the asymptote. At pi our value is also 1, but negative, and then follow the asymptote. And so there's our secant inverse graph. Imagine the derivative of this. How would we have a function that describes this? We have a split. There's going to be some domain issues that are restricted. That'll be something we'll have to take a look at. And lastly, our cotangent graph. Cotangent, very similar to tangent. So let's get a sketch here of cotangent. Just like tangent, we only need to look at a certain interval of it. Cotangent is defined as cosine over sine, so wherever sine is 0 gives us a problem. Well, that's a problem at 0, and at pi, and any interval of pi. So it kind of shifts where the asymptotes are by pi over 2 from our tangent graph. And then cotangent is 0 at our pi over 2, cosine is 0 at pi over 2, and then we have our sketch with this being pi. And remember, it goes on infinitely many times, so we can put that in as a rough sketch. See, it fails a horizontal line test for an inverse function. And so we need to restrict it. Well, most naturally, we're going to restrict from 0 to pi, a nice continuous curve. Why would I split this if I don't have to? So from 0 to pi is how we'll define cotangent inverse. Not including, the 0, because it's an asymptote, and not including the pi, also an asymptote. Then when I sketch out my inverse function, x-axis is now the asymptote like the y-axis was. Y equals x is our form for inverse, they switch. And then also at pi over 2, we're at our 0, so I guess we could draw in our pi over 4s, and that would be our 1 and our negative 1. And here is our cotangent inverse. All right, so we need to be able to understand which values we're going to use, and then also to be able to understand how we're going to use them for calculations. So let's take a look. Unit circle, really important, so I have it here for a reference. Now I want to talk about this word arc. Arc sine is just a fancy way of saying sine inverse. Why do you think we would have another way of saying that? What do you think people think about this as? A power. And when I think of powers, I don't think of the trig inverse rules. I think of power rule for derivatives, but it really represents something different. So we need to think about sine. Now, where does sine equal -1/2? Well, that makes us need to think, though, about where can we look. Sine, the values that we can have for an inverse function go from -π/2 to π/2. And so on my unit circle, I'm only going to look at -π/2 to π/2. Where does sine equal that -1/2? Sine, remember, is our y value. Sine is -1/2 here. 11π/6. That's not in my interval, but I could look at that as -π/6. And so that would be our answer. All right, the next one, arctangent of square root of 3. Well, tangent isn't on my unit circle. Square root of 3 I need to think about. Remember, tangent, just like sine, goes from -π/2 to π/2. And let's take a look at our unit circle. So we're looking at these values. Well, sine over cosine, 0. 1 over square root of 3. Well, what's 1 over square root of 3? Because the denominators really cancel each other out. I get square root of 3 over 3. Nope, this is just 1, square root of 3 over 1. There we have square root of 3, so it occurs at π/3. Arcsecant of square root of 5 over 2. Do we see a square root of 5 anywhere on our graph? Okay, so we are going to need to think about how we're going to work with this one, and sometimes making a triangle is going to be our best bet. Let's think about what this means. This means what angle gives me square root of 5 over 2? Secant is a ratio of reciprocal of cosine, and so cosine, if this is my angle, reciprocal, instead of being opposite or adjacent, over hypotenuse, we have hypotenuse over adjacent. And from there, what you would most typically see is you might have something like this. What is the sine of arcsecant of this? Well, what would we need to do to solve this one? So it's saying this is the angle, but now what is the sine at this angle? Well, we would need to solve out this triangle. Pythagorean's theorem. Square root of 5 squared, that's our c squared, equals 2 squared plus b squared. We get that this side is 1. And so then my sine of that angle would then be 1 over square root of 5, otherwise known as square root of 5 over 5. And so more often than not, you're going to see these as a compound value.